Everything's going all right? Everything good? Yeah. It is Friday, I know. Friday. It's exciting. Yeah. All right. So I asked you to look at the next two in the long division last time. So let's go over those quickly because we want to convert these long divisions into a different type of division on the next page. So we talked about long division last time. So remember that when we're doing the long division, basically we're putting the denominator into the numerator, right? Dividing the bottom into the top. So we'll divide the x minus 4 into that 3x cubed minus 16x squared plus 21x minus 3. What do we look at first? Yeah, we look at the 3x cubed, and what do we want to know? Yeah, so how many times what goes into the 3x cubed? The x, right? That piece right there, correct? We want to know what we need to multiply the x by to give us 3x cubed. What is that? 3x squared. Then what do? Multiply the 3x squared times the x minus 4, right? So in this case, we get 3x cubed minus 12x squared, right? Agreed? Okay. And then we subtract. When we subtract, what do we get? It'd be a minus 4x squared, right? Because we'll have a minus 16 minus a minus. So I'll add the 12. Yep, so we'll get a negative 4x squared. And then we on the 21x. Since I see lots of people writing things down, I see that you all worked on it as I asked you to between Wednesday and today. Yeah. What's next? What do we look at next? Yeah, we need the negative 4x squared. So what do we need to multiply the x by to get negative 4x squared? Yep, negative 4x, good. Multiply that through, we get negative 4x squared plus 16x. Subtract, we get good, 5x, and then bring down the minus 3. Almost done, right? What do we need to do now? Yeah, look at the 5x and the x. So what do we need to multiply by in that case? 5. Multiply by our 5. And subtract, and we get 17. Right? So that's our remainder. Again, how do we know what we're done? What are we looking at for our remainder relative to what we divided by? What has to be true? What tells us that we're done? Yeah, good. The power of x that's left here has to be less than the power of x that's up here, right? The degree of what's left has to be less than the degree of what we are dividing by. This is degree 0, because I can think about an x to the 0 there. That's degree 1. So we know that we're done. So finally, if we want to write this, we would write the quotient, which is 3x squared minus 4x plus 5, and then plus the remainder over what we divided by. So we can write that quotient as, or that fraction as 3x squared minus 4x plus 5, and then plus 17 over x minus 4. There's a couple of things I want to recognize about what we just did. First, notice that every time we're doing this subtraction here, we're canceling off that leading term. The important thing to keep track of is what we need to subtract off each time. So notice with our leading term here, we just know that we're going to subtract off that 3x cubed, if you will. Over here, though, we're left with that minus 4. How did we get the minus 4? We took the 4 times the 3, or the negative 4 times the 3, put it here, and subtract it down, right? So we got that -4, or that -4 there. The same thing here. How did we get this 5? We took the -4 times the -4, got the 16, and got the 5, right? These things in the front, we don't really need to keep track of because we know they're going to cancel each other out. The thing that's important are these computations. We're going to do that again here in a minute. The other thing I want to notice, and this is going to come up later, notice that if I put in, say my f of x is the numerator, and I ask you to compute f of 4, what do you get if I put 4 into this polynomial? What'd you get?
I had 17.
That's what you should get, a 17. Yeah. You notice anything with the 17 and something else that we see 17 in the problem? Yeah, right there, right? Wonder if that's a coincidence. Well, let's do the next one and see if it's a coincidence or not. See if I can get the screen to come back up again. Do the same thing with this one. It's a little bit longer, but it's all right. We can go through it. All right, so we're going to put the x plus 1 into the 4x to the 4th plus 2x cubed plus x squared plus 2x minus 8. What's first? Yeah, so what's going to go up on the top here? 4x to the 3rd, right? So we'll have 4x to the 4th plus 4x cubed. We multiply through. What do you get after you subtract? Yeah, -2x cubed. Bring the rest of it down. Make that actually look like a 3. What are we going to put up at the top now? -2x squared. Good. So we'll have -2x cubed minus 2x squared. Subtract. When we subtract, we get 3x squared, right? Because I got minus a minus, right? Got to remember to distribute the minus sign. What goes up at the top next? 3x, good. Multiply it through. Subtract. What do we get after we subtract here? -x, good. And so then what's going to go up top? -1. So we'll multiply that through. And when we subtract, we should get -7. Do me a favor, and if I say my f of x again is the numerator, see what you get when you put -1 into the function.
Anybody get a number?
-7.
I bet you get -7, yeah. So if I put -1 in for x, that'll make it a positive 4. -1 cubed will be negative, so 4 minus 2 is 2. We'll get a +1, so you get a 3. Minus 2 will give you a 1. Minus the 8 will give you -7. Again, notice any coincidence here, or what's not really a coincidence. Yeah, these should be the same. Okay. All right, so there's a couple of things that we should notice about this type of problem. What we're doing here, notice that we're dividing by a linear factor, and in particular, or a linear polynomial, I guess I should say. And notice in particular that coefficient on the x is 1. The other thing to notice is that notice in the previous problem, we divided by x minus 4. I had to plug in a positive 4. We divided here by an x plus 1. I had to plug in a -1. I can think of that x plus 1 as an x minus a -1. And again, notice that when we're dividing by these linear factors, these linear polynomials, when I have that leading coefficient of 1, the only thing I really need to keep track of is what's going on here as we subtract down. Or if I change it to a minus, I can think about just adding it down. So again, notice when we multiply the 4 times the 1, that's where that 4 came from, right? When we multiplied the 2 times the 1, that was where that 2 came from, and so on down the line. So when we're dividing by linear factors, we can do a faster process, which is known as synthetic division. So rather than giving a definition of the synthetic division, let's just do this example. Same idea, I want to do this division, but I want to do it a little bit faster. So here's how we're going to do it. The first thing I'm going to notice is this is my polynomial on top. I'm going to write down the coefficients. So the coefficients here are 5, -7, -15, and 38. Notice my denominator is an x plus 2. Up here in the upper left-hand corner, I'll do basically the opposite of what's there. I want to think of it as x minus something. So I'll put a -2 up there. So we have an x plus 2 in the denominator. We'll put a -2 up in the upper left-hand corner. The reason why we kind of flip the sign is, remember when we do our long division, we subtract down. If I flip the sign, then I can just add down instead. Takes care of the subtraction for us. Okay. All right, so here's the process. We're going to bring the 5 down. That first one you're always going to bring down, and then it gets very repetitive after that. We'll take the -2 times the 5 and get -10. Think about why we would have that -10 there. Well, notice, again, if we were doing the long division, you'd ask, what do I need to multiply the x by to give you 5x cubed? It would be 5x squared, right? So that's where that 5 comes from. Then you have to distribute that through. So I have to take the 5 times that thing, right? That's where that's coming in. Okay. We will add down. When we add, we get -17. And now do the exact same thing again. -2 times -17 gives us +34. Add down, we'll get a +19. Multiply, we get -38. And then add down, we get 0. I'm putting a little box around this. This is the remainder here. It's also what you get if you put -2 into the function, and you can check that. If you put if f of x is my numerator, if I'm called this thing my f of x, if you put -2 into the top, you get 0. You can check to make sure that you really do get 0. But you do get 0. You get what? -40
and then you'll have a plus 30, so that'll give you a negative 10, and then plus the 38 gives you positive 28, and over here you'll get negative 28. They'll cancel, so you really do get 0. So the synthetic division is a little bit faster. Notice that was pretty quick for us to do the f of that number, right? All we had to do is multiply and add, right? That's all we had to do to get to that value, rather than having to do those powers. The other thing is these numbers are the coefficients on your quotient. Okay? So we divided an x cubed by an x. What should we end up with if we divide an x cubed by an x? Not a trick question. If you divide x cubed by x, what do you get? X squared, right? So these are the coefficients on a quadratic polynomial. This will be 5x squared minus 17x plus 19. So this is equal to 5x squared minus 17x plus 19, and there is no remainder. We had a 0 remainder, right? So I don't need to worry about a fraction part on the end. So that's how that's a simplify. This is leading into the stuff that we're going to do in the next section to find zeros. Remember again, when you plug a number into a polynomial and get 0 out, that's what we refer to as a 0 of the polynomial. Okay? We're going to use synthetic division to help us find these zeros a little bit faster. So let's see if we can do the next one. This one's slightly different. We're going to do lots of these problems, by the way. We're going to have plenty of practice with doing synthetic division. We're just going to use it in the context of doing other problems. We've got a 6x to the 4th, a minus 59x squared, and a plus 2. You should notice something different about that numerator that hasn't happened in the other numerators. In particular, what's missing? If you think about missing pieces, what's missing in the numerator? The x cubed and the x, right? So when you're doing synthetic division, just like when we said if we had missing terms when we did long division, you put a 0 in there for that term. Do the exact same thing for synthetic division. So when you write your terms across, your coefficients across the top, I'm going to put a 0 in where the x cubed term would be, and I'm going to put a 0 in where the x term would be. So it's 6x to the 4th plus 0x cubed minus 59x squared plus 0x plus 2. Okay? Since I've got x minus 3 in the denominator, what's going to go up in the upper left-hand corner here? A positive 3. Good. And now again, the process is bring down the coefficient. First coefficient, bring down the 6. And then it's repetitive. What do I do next? Multiply and get 18. And then, yep, add, good. 18. And then 54, good, yep. 18 times the 3 gives you the 54. Add down, you get negative 5, and then we negative 15, add down, negative 15, multiply, negative 45, and add down, we'll get negative 43. Okay. So again, let's ask a couple of questions before we write kind of a final answer as how what the fraction kind of breaks up into. Is 3 a 0 of the top? Does when we plug in 3, do we get out 0 into the top? No. What do we get out? What do we get out of the top if we plug in 3? Negative 43, right? So again, the value we get at the end, this is f of 3 if my numerator is what I'm thinking of my f of x. Okay? And again, that's a lot easier than, I mean, you can check it. You can plug 3 in there and see that you'll get negative 43. So like I said, this is leading us into new stuff that we're going to talk about in the next section. This tells us that 3 is not a 0. Okay? All right. So then when we write our answer here, I'll write it below instead of up at the top. What's the quotient going to be?
we started with x to the fourth, we divided by x. So this first term in your quotient will be what? Yeah, so it'll be an x cubed, and in particular it'll be 6x cubed. Good. The next term will be 18x squared. The next term will be negative 5x. The next term will be negative 15. And again, this number on the end is your remainder. Remember how we write the remainder? We do remainder over what we divided by. So it'll be minus 43 over x minus 3. What questions do you have on this one? Or either of these two that we did? Is okay? All right. So this is, pardon me, this number 7 here that's listed on here is doing the exact same thing. Use your synthetic division, and all it's asking you to do is figure out if 2, you plug in 2, you get out a 0, what you get out when you plug in 2, going through your synthetic division. So do that real quick. Do it just like we did the previous problem. Just use a 2 up in the upper left-hand corner and see what you get when you get done. Ready to chat about it? All right. So what did you put across the top for your synthetic division? Good. And then the upper left-hand corner, we put 2. Yeah. First step. Yeah, bring down the 2, right? And then times it by 2 to get 4. Okay. Good. Is that what others got? So notice after you do that first step, everything is repetitive, right? You multiply, add, multiply, add, multiply, add, until you get done. Right? So what does that 0 tell you at the very, very end? Yeah, so f of 2 in this case is 0. So is 2 a 0 of the given polynomial? Yes. So remember again then, if 2 is a 0, what has to be a factor? If 2 is a 0, then what's the factor? Talked about this last time. Think about if you set it equal to 0 and you factored it, how would you have gotten a 2? What would you have had to have seen the factor? X minus 2, right? So when something is a 0, x minus that number has to be a factor, right? Okay. So in particular, one way you could write, this is where we're headed in the next section. In particular, we know that 2x to the 5th minus 5x to the 4th minus 3x cubed plus 8x squared plus 11x minus 14 has to be x minus 2 times something, right? What's left over is that quotient that we just found. So we've got those numbers, the 2, the -1, the -5, the -2, the 7. We divided an x to the 5th by an x, so we know we would be left with x to the 4th. And those are the coefficients of that fourth degree polynomial. Like I said, this is where we're headed in the next section. So when you have something that is a 0, x minus that number has to be a factor. Okay? So let's see if we can use that knowledge to help us answer the next question. But before then, did you have any questions on this one? Are we okay with doing those computations? We're going to do a bunch more of these because this is the technique we're going to use to help us find zeros here in a little bit. Is this okay? Okay. So let's look at the next one. We're going to ask you to construct a 4th degree polynomial with these zeros. All right. So 4th degree polynomial, we want x to the 4th when we're done. I want zeros of x equals 1, or of 1, -1, 2, and -2. So again, if 1 is a 0, what has to be a factor? If 1 is a 0, then what has to be a factor of the polynomial? X minus 1. If -1 is a 0, what has to be a factor? X plus 1. So now do you think we can figure out what the factors have to be? Using those 4 zeros? Tell me what they are. You just told me 2 of them. X minus 1 and x plus 1. What are the other 2? Good. X minus 2 and x plus 2. Good. There we created a 4th degree polynomial. Why do I know it's 4th degree polynomial? Yeah, once we multiply it all out, this would give you an x to the 1st times an x to the 1st times an x to the 1st times an x to the 1st, right?
Yes. We can just leave it like that. We don't have to. Are we going to factor it out? Or?
This one we could multiply out pretty quickly. Most of the time we'll probably just leave it. I don't know. But notice when you multiply the x minus 1 times the x plus 1, what do you get? It's just x squared minus 1, right? Because it's a difference of squares. And the other one's going to be what? Minus 4, right? Because I got to square the 2, right? And then if you multiply, this one would just be FOIL. Then you would get x to the 4th minus 5x squared plus 4 when you're done. That's how it wasn't horrible to multiply out. But that's how we construct that polynomial. It told you what the zeros were, so then x minus that has to be a factor. That okay? Now the last one's got a little bit of a twist to it, but we'll talk about how we find the twist. Ignore the last part, where it says the y-intercept piece, because that's going to be the twist. Let's start this problem exactly like we just did the previous one. It says construct a 3rd degree polynomial. And we have zeros of -3, 2, and 5. So if I ignore the last part, what would you write down? Yeah, x plus 3, good. Good, x, yeah, exactly right. That's exactly what we'd write down. Leave a little bit of a space after that equal sign, by the way. We'll talk about how what we're going to fill in that space with here in a second. Okay. Are we okay with that part, though? Given the zeros, we found the factors. Is that okay? Okay. Now let's go back to that little twist part, that extra piece of information they gave you. We want a y-intercept of 0, 120. How do you, in general, how do you find a y-intercept for a function? What do you do?
X equals 0.
Yeah, make x equal to 0 and figure out the y value, right? What do you get when you plug 0 into that function? What value do you get out? The way we have it right now, what do you get out when you put 0 in for x? You get 30. What are we supposed to get out? We're putting out the 120, right? Because that's what we want for the y-intercept, right? So here's how we handle that. Notice I said leave a little space here. Remember we did all the scaling stuff, right? We could scale with a number out in front. Does a multiply, right? Does a vertical stretch or a compression, depending on how we want to do it, right? Let's make that an A, and we're going to solve for what the A has to be. You just told me a second ago, when you put in 0 without the A in it, you got 30. So if I put 0 in there, I get 30A. Right? What are we supposed to get out? What does it tell you the y-intercept is? 120. So what does A have to be? 4, yeah. Okay. So then your polynomial would just be 4 times x plus 3 times x minus 2 times x minus 5. Hardly. And no, you don't need to worry about multiplying that out. Is this okay? Do this with a vertical scaling. Don't do it with a vertical shifting. If you try to shift the polynomial to the right spot to change the y-intercept, you're going to move the zeros because you're going to shift it off the x-axis. Okay? Do it with a scale. Because what happens when you multiply 0 by a number? What do you get? When I multiply 0 by a number, I get 0, right? So vertical scaling doesn't change your zeros, right? Okay? So do it with a vertical scale, in this case, when it asks you to change that. This okay? So that's how you handle those, creating the, then they'll get, like I said, the only little twist is you might have to change that number in the front. Anything that asks you to create a polynomial like this, you're going to make the factors out of it from the zeros. So they all look like that. All right. Questions before we go on to, basically, I'm going to say new stuff, but it's really just a continuation of what we've been talking about. So in the next section, like I said, this is actually the next couple of sections, our whole goal is to try to break down the polynomials as much as possible. Try to factor them as much as we possibly can. Because think about how you solve equations, generally speaking. You always try to factor, if you set it equal to 0, and factor, because then you can set each piece equal to 0 and get what the answers are supposed to be. So that's why we're worried about doing this factoring stuff and finding these zeros, is so that we can get all of the zeros, to get all of the solutions to a polynomial. That's not what I want. Now, we know that not every function necessarily crosses the x-axis, but there are still some things that may make it equal to 0. So to help us get some of these zeros, we need to do a little bit of stuff with complex numbers to be able to get all of the answers, all of the zeros of a polynomial. And I'll talk about what I mean here in a second about, we know that some of them just don't cross the x-axis, but there still might be zeros to them. So just to review a little bit of complex numbers, we refer to the number I as what's called the imaginary unit. And generally, we think of that as the square root of -1. Now, why do we think of that as the square root of -1? Well, the imaginary unit came about when trying to solve an equation that looks like this: x squared equals -1. In the real numbers, we know that if we square a number, can we get a negative? No. Okay. So the imaginary unit was introduced to help us solve equations that don't have solutions in the real numbers. Okay. This has been done throughout history, by the way, with trying to solve equations. Negative numbers, when they were first introduced, were used to solve equations. And a matter of fact, back when they were used, they were called not negative, they were called absurd. Because when we were talking about trying to solve these equations back in ancient Greece, negative numbers didn't have much context to them because what they were doing were counting things, right? Or dividing up physical things, okay? They were okay with positive numbers. They were okay with fractions. But negative things didn't make any sense to them at that time because they didn't see any applications to negatives. But they knew that they needed negatives to solve things like 2x plus 5 equals 0. You need a negative number to solve for that, right? If you do 2x plus 5 equals 0, I got to subtract the 5 and get a negative on that other side. Okay? But again, of course, we know lots of applications of negative numbers now, right? Think of this as simple ones, right? If you go bank balance and it's positive, that's good. If it's negative, that's bad, right? You owe somebody money, okay? So you can think of lots of different applications of negative numbers, and we all are used to using them and are fine with them, whatever. That negative means something. For example, if you're doing directions in physics, positive means up, negative means down, okay? So there's lots of applications of negatives. When imaginary numbers were first introduced, again, it was to solve these equations, but they didn't see much of a physical use for imaginary numbers. It was this number, it's great, we can solve these equations, but I don't see a reason why we have it other than to solve these equations. Now, complex numbers pop up in all sorts of applications. For example, you'll see them if you see them in physics to be able to solve things with waves. If you do anything with waves, imaginary numbers pop up. Okay. So there's a lot of instances in math where things are given a negative connotation to them because when they were first introduced, there didn't seem to be a lot of application to them, and then the names stick, and we find out, hey, by the way, this wasn't so bad. Imaginary is one of those words. But think about there's negative, improper, irrational, imaginary, right? All of those are words we use in math that typically have negative connotations to them, but there's not really any negative things to them at all. All right, anyway, I'll get off my soapbox from the history of math lesson there. All right, so when we talk about a complex number has a real part and an imaginary part. So we can write complex numbers in the form of a plus bi, where your a and your b are real numbers. So this is what we mean by a complex number. And this is usually what we refer to as a standard form of the complex number. You write the real part, the part without the I in it first, and then the imaginary part, the part with the I in second. Okay? All right, so let's talk a little bit about how we play around and simplify with these things, making sure that we remember complex number arithmetic before we start using them to introduce them into zeros of polynomials. So if we wanted to evaluate something like the square root of negative 169, what I would encourage you to do every single time, take care of the negative under the radical first, and then simplify like you would do any other radical. So if I take the negative out, that gives me an I times the square root of 169. Square root of 169 is what? It's 13? Yeah. So that would just be 13i. You don't have to write this next part down, but if I wanted to be really, really pedantic about it and write it in standard form says real number plus imaginary number, right? So in standard form, that would be 0 plus 13i, like that. And technically, standard form says that you write the number in front of the I. Typically, if we have something with a square root left in it, we would write it after the I. So what I mean by that is, if I look at the next one, I take care of the negative first, make it an I. So I have I times square root of 27. 27 is 9 times 3. So if we simplify that, we would get what? Yeah, so we got a 3 root 3 there. And usually, a lot of times, you would write it this way. Put the 3 in the front and the root 3 after it. It looks weird to put the root 3 in front of the I, because then it might be confusing of whether the I is under the radical or not. But technically, in standard form, the root 3 would need to be in front. Is this simplifying okay? Okay, cool. All right. We said that we could write any complex number in that form of a plus bi. Notice we don't have an I squared or an I cubed or anything along those lines, because we know that I squared is equal to what again? I squared is -1. Remember, that's the solution to this equation back up here at the top. Okay? So if you're asked to simplify powers of I, there must be either an I in it or not. There's not any power of I besides 1 that we can use. Okay? So the idea here is looking at a pattern. Well, certainly anything to the 0 power is what? Anything to the 0 power is 1, right? Yep. Okay. I to the first power would be I. You just told me a second ago that I squared was -1. If I do I cubed, well, I can think of that as the same thing as I squared times I. What is I squared equal to again? -1. So this just simplifies to -I, right? Let's do I to the 4th. I can think of that as I could do either I cubed times I or do I squared times itself. What did you tell me that I squared was equal to? -1. -1 times -1 is 1. Yeah, so this simplifies to 1. How about I to the 5th? I can write that as I to the 4th times I. What did we just say that I to the 4th is equal to? 1. So this just simplifies to I. I to the 6th. Well, that's I to the 4th times I squared. You told me I to the 4th was equal to, and I squared is equal to -1. So we end up with -1. Looking at these two columns, we got first column was 1i, -1, -I. This next column is 1i, -1. Any guesses on what this is going to be? -I. Yeah, there's a pattern, right? I'll go through it one more time here, but I to the 4th times I cubed. I to the 4th was 1. I cubed was -I. We just get -I, right? So you see the pattern? What do you think I to the 8th is equal to? 1. I to the 9th. I to the 10th. -1. I to the 11th. -I, right? It's just rotating around, right? It's just cycling. Okay. What do you notice about these exponents here? 0, 4, 8. They are multiples of 4, right? This is 1 more than a multiple of 4, 2 more than a multiple of 4, 3 more than a multiple of 4. So basically, we could just look at the remainder when we divide by 4. Okay? So we've already computed I to the 9th. We did that the longhand. But what if we want to do I to the 23rd? When I divide 23 by 4, what do you get for a remainder? It's 3, right? 4 times 5 is 20, and you get 3 left over. If you don't want to try to figure it out in your head, use a calculator. Get 5.75 in your calculator. What part of that represents your remainder?
The 5 or the 75?
Sorry.
Yeah, this part does, right? That's 3/4. The remainder is 3. Right? All right, so the remainder is 3, so this must be the same thing as I cubed. So what did you just tell me I cubed was equal to? Negative I. Good. When I take 124 and divide it by 4, what's your remainder? Again, if you need to use a calculator, that's fine, but what do you get when you divide 124 by 4? 31. Is there any remainder? Is there anything past the decimal point? No. So this is the same thing as I to the 0, which is 1. Good. If I do I to the 376, what do you get for remainder? I think you get 0 again, don't you? Yeah. So it's I to the 0, which again will be 1. Again, you can do this in your calculator. Do the division in your calculator. Take the exponent divided by 4. If there's nothing after the decimal place, the remainder is 0. If there's a 0.25, what do you have a remainder of? 0.25 is a quarter, so the remainder would be 1. If you have 0.5, the remainder will be, so it'll be negative 1, and the remainder will be 2, right? It'll be I squared. And then if you have a 0.75, the remainder is 3, so it's an I cubed. You can do it on your calculator. You just divide it real quick and figure out what the decimal part is. That tells you the remainder. It's either 0, 1, 2, or 3, so you only have to remember the 0, 1, 2, or 3. We need some flappers. Is that okay? All right. Doing some complex arithmetic is going to be important as we're doing some of our synthetic division that involves with some of these complex numbers. Good news is that most of it is just like what you do with polynomials. The only thing that's weird is division. If these were x's instead of i's, what would you do when if you wanted to add or subtract? What would you do? If they were x's instead of i's, what would you do? What would you get for the first one? Yeah, that's right. Yeah, I would just add my 15 and 3. I would add my -7 and -14, right? Those are the like terms. It's literally the same thing you do for complex numbers. It's not any different, okay? So for complex numbers, you would just combine like terms. So you get 18 minus 21i. That's it. Literally not any different, okay? Same thing for subtraction. What would you get for the subtraction here? -3. Yeah, plus 11i. I got to distribute the minus sign through, right? But it's just like what you do with polynomials, isn't it? Literally zero difference to that, okay? You do literally the exact same thing when you add and subtract. We do the exact same thing when we multiply. There's only one extra little step that we have to do at the end. Okay? So if you were asked to multiply these out as polynomials, what would you do? You just FOIL it, right? What would you get when you multiply it out? 3 times 5 would give you 15. 3 times 4i, 12i. -2i times 5, -10i. -2i plus 4i would give you -8i squared. That's what it would be as polynomials, right? It's literally what you get, isn't it? Okay? The only extra thing we do now is what's I squared equal to? -1. So instead of -8i squared, that becomes +8, right? Because I squared is -1. So it's just the I squared goes away and it flips the sign. And then 15 plus 8 gives us 23. And notice I combined the like terms with the i's, right? Plus 12i minus 10i gave us plus 2i. Does that make sense?
Is that okay? There's literally, it's not any different than multiplying polynomials, is it? So what would I need to do if I want to do 8 minus 3i squared? If you need to, write it out this way. What would you get? What would we get here? So we're out of time. What would we get? Oh yeah, just go ahead. Just tell me. Yeah.
64 minus 24i minus 24 plus 9i squared.
Good. That's what we get when we FOIL, right? 8 times 8 is 64. 8 times negative 3i is negative 24i. Same thing in the middle. Plus 9i squared. 9i squared becomes negative 9. And then subtract, and you get what? 55 minus 48i? I get it right. Okay. That's not any different than doing polynomials, is it? Okay. All right.